Hello, everybody. I would like to, this is for the course at University of New South Wales, MATH2099, and it is about linear algebra, and we are going to go through the solutions of the question 32. Now, in these questions, we have a linear function from t to t, and given the matrix by A. This is the matrix representation for t. This is with respect to the standard basis in R2. We would like to find the matrix T with respect to the basis B, which is another basis of R2. So in order to be able to do that, we are going to use the following theorem. So if we have a linear transformation T to the n to the R to the n, and A is a matrix form for the transformation T with respect to the standard basis of Rn, and B is another basis, and construct the matrix B, whose columns are the vectors in B. And then by calculate the B inverse, and then multiply B inverse AB, and the matrix that you're going to get is the matrix of T with respect to the base B. So this is, and also you can multiply from this side by B, from this side B inverse, and of course, A is equal to T. This is the T transformation with respect to the basis B, and we are multiplying B from here, B inverse from here. Then we are finding the matrix form for T for the standard basis of A. So you can go both directions. So this theorem does not tell you exactly one direction. It tells you the both directions, okay? Standard basis to another basis or another basis to standard basis. If you're dealing with a standard basis to another basis, this is the formula. If you want to find out matrix form from the, the matrix form with respect to the non-standard basis, then you can find out the matrix form for this linear transformation with respect to standard basis by using this formula. These two are equivalent together. Okay, let's do this example. Now, this is a matrix form with respect to the standard basis, and this is another form. So we would like to find out the matrix form for this linear transformation with respect to this basis. That's the idea. So it says that the theorem says that construct a matrix B whose columns will be the vectors of the basis vectors. So the basis vector, we have 1, -1, 3, 2. That's what I'm doing. This is 1, -1, 3, 2. These are the columns, are the basis vectors of B. Then, as the theorem says, I'm going to find out this multiplication. But before before doing this multiplication, I need the B inverse. You can calculate the B inverse in the way that we calculate it in general as well, if you like to, like saying that B and I, and then you can apply the row operations, and then you will find the identity matrix, and the other matrix that you're finding on the right-hand side will be the inverse of B. This is a general form that how we find out the inverses. But the 2x2 matrices are extremely easy. We don't need to go through this process at all. It is very obvious. You can memorize this as well if you like. It is because you're multiplying this times this. This is the determinant of the 2x2 matrices, AD minus BC. If you multiply this row with this column, you see AD minus BC, which is when you're dividing with this one, you will get 1 in this position. And this multiplication by this one, you have AB minus AB plus AB, then you will get 0 for this position. What I'm saying is that if you multiply this matrix with the ABC, multiply this matrix with the ABCD, you will find that identity matrix is very straightforward. So I'm going to use this formula rather than doing usual way. As I said, you can memorize this. It is very straightforward. As you see, this is a determinant. You are swapping these two positions, AD, and you are getting minus for this position. This is the inverse of a 2x2 matrices. If you haven't realized that before, that's the way to go. So for us, this is the matrix that we would like to calculate to be inverse. And as you see, it is just a one line. By using this formula, this times this is 2, and this times this is minus 3 times minus 1. That will be plus 3. So 2 plus 3 is 5. So this is the determinant. And I need to swap these two entries. This is 2, 1 in that moment. And this entry will be minus, and this entry will be minus. This is minus 3, and this will be plus 1. This is exactly what it says. I hope it is clear. And the determinant is this. This is how I've done the determinant. So this is B inverse. So we will just write it down, all these matrices, and multiply. So that is the B inverse here. This is A here. A is given matrix here. As the questions 4191. This is A. So this is A. This is B. If you multiply these two matrices, this row with this column, it will be 8 minus 3. This will be 5. 2 times 9, 18. 18 minus 3 is 15. This times this is 4 plus 1 is 5. This times this, 9. This times this is 1. So together is 10. So the multiplication, these two, gives me this matrix. Now let's multiply this matrix with the B now. This row with this column. So before multiplying, I just multiply with the 1 over 5 because we have too many 5s. This is 1, 1. This is 3, 2. Right? This is how we got that. And then multiply with this. This row with this column, 1 minus 3, that will be minus 2. 3 plus 2, 1 plus 3, and 6. 6 plus 3 is 9. This is 1 minus 2, that will be minus 1. This times this will be 3 plus 4, that's 7. So as we know, matrix multiplication row by column, right? I hope this is clear for everyone, but let me right? This is this column vector with this row vector with this column vector gives you this entry and so on, right? And then this row with this column will give you this entry. This row with this column will give you this entry. I hope this is clear for everyone. So this matrix here is the matrix of the linear transformation with respect to the basis B. This is how we change the matrix form from standard basis to non-standard basis. That's all for this question, and thank you very much for listening.